So next part is deducing the full adder from the MUX IC 74153. Here is a circuit diagram of full adder. We have to do the biasing from pin number 16 and pin number 8 to the ground. Okay. Rest are the connections which have to made on this digital IC trainer kit here. So let's just make the connection now. So students, as you can see, the first set of the input will provide the sum part always, and the second set of input always provides the carry part. Now let's just first do the biasing. From our previous experiments, I hope that you already know where the pin number 16 will lie at this side of the port. Here you can see the biasing is done. Next will be our connections which are given to the ground part. So I am connecting all the connections which are to the ground part here. So here, as you can see that we have 1, 2 and 3 ports which are connected to the ground. I have connected those 3 ports here, 1, 2 and 3 ports. Okay. I hope in the circuit diagram you are well aware that which pin is connected to where. I am quickly connecting all the connections from this circuit diagram. Okay. Then we will realize if it satisfies the truth table or not. And the circuit diagram is same as the half adder part you have seen in the previous. Okay. So I am quickly connecting all the connections here. So students, this is the circuit diagram of full adder. This is the circuit diagram of full adder. This will look like this. The NOT gate biasing. Okay. And the output part. Check. Take this input 0, 1, 0, that is A provided 0, B 1 and C 0 logic. Then some part will be 1, that is the red color wire LED should glow up, and the carry part will be 0. So here this is 0, this is 1 and this is 0. Okay. You can see here the sum part LED lights up. Now let us take another example with the carry LED glowing up. We have to take 0, 1, 1 and this input of 0, 1, 1 will cause the carry input LED to glow up. That means the black color wire LED should glow up and the red color wire should be off here. So now let's just check it. We have to provide 0, 1 and 1. Okay. You can see here the black color wire LED glows up here. That means the carry part is glowing up. The carry logic is 1 when we have provided 0, 1, 1 as the input. Okay. In the output you can see that the carry LED glows up. That means the black color wire LED glows up. For further verification, let us take, if I provide all the input to the logic 1 here, then the sum will be 1 and the carry will be 1. That means both the output LEDs should glow up. Let's check them. If I provide 1, 1 and 1, okay. If I provide 1, 1, you can see that both the LEDs are glowing up. So this means that we have verified the full adder circuit using MUX IC 74153 here. Thank you. Okay, now let us discuss it. 0, 0 means I have to select I node, right? 0, 0 means I have to select I node. Okay. So for these two I have to select I node and the input will be 0 and 1. For 0 input, sum and carry both are 0, but when I provide input 1, then the sum part will be 1 and the carry part will be 0. So look here. From here I am providing 0 0, that means I have to focus on I0 and I0 for sum part and for the carry part here. If I am providing logic 0 means I0 is at logic 0, so the sum will be 0 and the carry part is connected to the ground, so the carry will be 0 also. Then we have to provide input A as logic 1. If I provide logic 1 to the input, see here the I0 part is 1, that means the sum will be 1, and again you can see that the carry is connected to the ground part, so that means the carry is 0 here. This satisfies the truth table. Alright, the next example I am taking. When I provide B and C in 1 1, that means I am focusing on I3 port, and the input which I provide is A to the logic 0 and A to the logic 1. When I provide logic 0, the sum will be 0 and the carry is 1. You can see here the carry is still 1, but when I am providing logic 1, the sum part changes from 0 to 1. Let's see here in the figure. You can see when I provide logic 1 1, that means I have to focus on I3 and I3 part only. You can see when I provide input A to the logic 0, the logic 0 will come here, so the sum part will be 0. For the carry part, you can see that I3 is connected to VCC. It doesn't depend upon the input A, so the carry part will be 1. Now if I provide input A to the logic 1, the logic 1 will arrive here. That means the sum part will be 1 and the carry part will be 1 as it is connected to VCC. So this satisfies the circuit and our truth table is satisfied. So you can say that the B and the C inputs are only for the selection part. That is, if 0 0 is given, I0 is selected, 0 1 is selected. Okay, these are for the selection part of I0, I1, I2 and up to I3 here. Alright, the first set of input used to find the sum and the second set of input is always used to find the carry output. Alright, and A is the input which we are providing with logic 0 or 1 to see the variation here.